looks odd, doesn't it? It doesn't look like it can manage the load it's carrying. As we've all seen, trucks need wide tires. On the other hand, let's look at a housewife trying to chop vegetables with a thick, blunt knife. She's not having much success. To chop efficiently, she needs a knife with a sharp blade. What is the significance of the width of the tires and the sharpness of the knife in these cases? This can be explained through the concept of thrust and pressure. The truck needs wide tires to reduce the pressure of the cargo. The knife needs a sharp blade to increase the pressure exerted on the vegetables. In this lesson, you will learn about thrust and pressure, with special emphasis on thrust and pressure in liquids. At the end of this lesson, you will be able to define thrust and pressure, differentiate between thrust and pressure, calculate thrust and pressure in given situations, explain the effect of pressure exerted by fluids, derive the expression for calculating pressure in fluids, state Pascal's law, and explain the applications of Pascal's law. Thrust is a vector force acting normally on a surface and is denoted by F. For example, consider the simple act of driving a nail into a wall with a hammer. The force that you exert on the hammer during this activity is thrust. Thrust is measured in dyne in the CGS system, and Newton denoted by N in the SI system. We have seen that nails have pointed tips to help us drive them into surfaces. Why is it important for a nail to have a pointed tip? For that matter, why is it important to have a sharp knife to chop vegetables? The force you apply in driving a nail or chopping vegetables is translated into pressure, depending upon the surface area of the object on which the force is applied. In other words, pressure is the amount of thrust acting on a unit area. Pressure is denoted by the letter P. Hence, pressure is calculated by dividing thrust with area. The lesser the surface area of an object, the more the pressure applied by that object. The pointed tip of the nail minimizes the surface area of the nail on which thrust is applied. Therefore, while driving the nail into the wall, the pressure of the hammer is maximized, which helps drive the nail into the wall. Pressure is scalar and is measured in dyne per centimeter square in the CGS system, or Newton per meter square, or Pascal, denoted by PA in the SI system. Another example will help illustrate further the distinction between thrust and pressure exerted by a body. Take a piece of foam and two identical metal blocks, say A and B, weighing 300 grams. The length, breadth, and thickness of these blocks are 30, 20, and 10 centimeters respectively. Place the metal block A vertically on the foam and the other iron block B horizontally. Now let's compare the compression of the foam where blocks A and B are placed. The foam shows more compression where the metal block A is positioned vertically. Considering that both the blocks have the same length, breadth, height, and weight, Why do you think we see this difference in the compression of foam? This difference can be attributed to the difference in pressure exerted by each block. Block A was placed vertically over the sheet of foam, while block B was placed horizontally. The surface area of block A in touch with the foam is 200 square centimeters. On the other hand, the surface area of block B in touch with the foam is 600 square centimeters. Using the formula for pressure, we can now calculate the pressure of blocks A and B on the foam. The pressure of block A on the foam is 1500 dyne per centimeter square. The pressure of block B on the foam is 500 dyne per centimeter square. Thus, in block A, the same thrust was acting on a smaller surface area. Hence, the pressure exerted by block A was higher. This explains why the foam showed more compression where block A was placed. The thrust exerted by a body remains constant, placed in any position. However, the pressure exerted by the body changes with a change in positions. Let's look at another everyday example. You may have used chairs in which the seat is created from plastic wave. These chairs are quite safe to sit on. However, if you try standing on such a chair, the plastic wire may give way under the strain. This is because when you stand on the chair, the area of contact becomes much smaller, and the pressure on the wire crosses the safety limit. In both the cases, the weight of the man, that is the downward force acting on the chair, is the same. However, the area on which it is acting has changed, leading to change in pressure exerted on the seat of the chair. So far, we looked at the examples of thrust and pressure in solids. However, thrust and pressure are equally applicable to the other states of matter, liquids and gases. Liquids and gases are collectively referred to as fluids. Since all fluids have the tendency to flow, like solids, fluids also have weight, and this weight exerts a force on the walls and base of a container. We can demonstrate the effect of pressure in liquids through a simple example using a plastic bottle. Fill the plastic bottle completely with water. Then make a small hole in the lower half of the wall of the bottle. You will see that the water gushes out through the hole with considerable force. This force is due to the pressure of the fluid at that point. So, how do we calculate pressure in fluids? To derive an expression for pressure in fluids, let's consider a beaker filled with a fluid, say water, of density D, to a height h. Drop a coin with the area of cross-section A into the beaker. The volume of the water column above the coin V is equal to area of cross-section of the coin multiplied by the height of the water column. This gives us equation 1. Volume V is equal to A multiplied by H. The mass of the water in column M is the product of the volume of the water and its density. Thus, M is equal to V multiplied by D. Substituting equation 1 in the expression for mass, you get equation 2. That is, M is equal to product of A, H and D. As you know, weight of a substance is a product of its mass and the acceleration due to gravity, G. Therefore, weight of the water column, W, is equal to the mass of the water column multiplied by G. Thus, W is equal to M multiplied by G. Substituting equation 2 here, you get equation 3. Weight of the water column acts normally on the object. Thus, the pressure P acting on the coin is the ratio of weight of the water column to the area of the coin. That is, P is equal to W divided by A. From equation 3, we know W is equal to product of A, H, D and G. This gives the expression of fluid pressure P. P is equal to HdG, where H is equal to height of the water column, D is equal to density of the water, and G is equal to acceleration due to gravity. Using this expression, you can calculate the pressure applied by a fluid in the walls as well as the base of a container. The pressure at a point in a fluid is equal in magnitude in all the directions. Now let's look at some applications of the concept of pressure in our everyday life. You may have seen a warning at the back of trucks moving on highways. Caution: air brakes maintain 50 feet distance. So, air is used in applying brakes for these huge vehicles? Amazing, isn't it? In fact, the hydraulic brake system used in cars also involves usage of a fluid brake oil. Both these applications, air brakes and hydraulic brakes, are based on a law related to pressure. This law is called Pascal's law. Pascal's law states that a change in the pressure of an enclosed incompressible fluid is conveyed undiminished to every part of the fluid and to the surfaces of its container. Let's conduct an experiment to verify Pascal's law. We take a container with two openings of unequal cross-sectional areas. We fill this container with water and then close the openings with airtight pistons, 1 and 2. Then we push piston 1 inwards. As piston 1 is pushed inwards, piston 2 moves outwards. Thus, the increase in pressure through piston 1 is conveyed undiminished through the liquid to piston 2. As the area of cross-section of piston 2 is greater than that of piston 1, the thrust exerted on piston 2 is greater than that on piston 1. Hydraulic brakes as well as air brakes operate on the same principle. Let's see how this principle is applied in the construction of hydraulic brakes. A hydraulic brake system consists of a brake pedal, a piston, a master cylinder, 4 hydraulic lines, 4 brake cylinders, 8 brake pistons, 4 wheels, 4 restoring springs. Now let's see how hydraulic brakes work. The master cylinder and the brake cylinder are connected to a thick copper pipe called the hydraulic line. thick brake oil is filled in the master cylinder and the brake cylinders, and they are fitted with airtight pistons. The master cylinder is connected to the brake pedal. A brake cylinder is connected to the metallic rim of each of the wheels. Now let's see how this arrangement of hydraulic brakes works to enable a driver to stop a car when driving. When the brake pedal is pressed, the piston in the master cylinder goes enforcing brake oil out with some pressure into each of the brake cylinders. At each brake cylinder, two opposed pistons attached to brake shoes are forced outwards. The outward movement of brake shoes presses the brake bands against the inner surfaces of the wheels to stop their rotation. When the brake pedal is released, the restoring springs at each wheel restore the pistons to their original positions. Thus, hydraulic brakes in automobiles employ the concept of pressure to enable drivers to stop heavy vehicles by applying a relatively light touch on the brakes. This brings us to the end of the lesson on thrust and pressure. In this lesson, you learned about the concept of thrust and pressure, the expression to calculate pressure in a liquid, and applications of thrust and pressure. The section on solved problems provides you an opportunity to review some model problems based on these concepts. To revisit the key points covered in this lesson, please review the flashcard. An instrument used to measure atmospheric pressure. Fortin's barometer is a modified form of Torricelli's simple barometer. Fortin's barometer consists of a narrow glass tube of length about 90 centimeters. This tube is closed at one end. The tube is completely filled with mercury and kept inverted in a cistern filled with dry mercury. Usually, the glass tube is protected by enclosing it in a brass tube. The upper part of the brass tube has a slit that enables the level of the mercury in the glass tube to be seen. A scale graduated in millimeters is attached to the brass tube. This functions as the main scale. For accurate measurement, a vernier scale that can slide over the main scale is also fixed to the barometer. The vernier scale can be moved up and down using a screw. The bottom of the cistern is like a bag made of flexible leather. The mercury level can be adjusted by means of a screw provided underneath. There is an ivory pointer in the cistern placed at the top. The tip of this pointer coincides with the zero of the main scale. The level of the mercury column in the cistern can be changed with the screw under it. It is so adjusted that the ivory point is exactly at the surface of the mercury in the cistern. The whole apparatus is fixed in a vertical position. Let us now see how it works. Any change in the atmospheric pressure is accompanied by an immediate change in the level of the mercury in the glass tube. As the height of the mercury column in the barometer changes, mercury flows between the tube and cistern. As a result, the level of the mercury in the cistern also changes. To determine the length of the mercury column in the barometer, it is necessary to know the position of the free surface in the cistern as well as in the tube. The first step in measuring atmospheric pressure using Fortin's barometer is to set the mercury level in the cistern. Using the adjustment screw, set the level of the mercury in the cistern such that the ivory pointer just touches the mercury. The reading of the top of the mercury column is then measured using both the main scale and the vernier scale. Before the readings are noted, the vernier scale needs to be positioned properly. The vernier scale is to be adjusted so that its edge and the corresponding reading in the main scale just set tangentially to the meniscus. Now, the readings on the main scale and the vernier scale are noted, and the atmospheric pressure is calculated. Fortin's barometer is widely used in laboratories and in meteorological departments. The main advantages of Fortin's barometer are: it is portable. It allows the mercury level in the cistern to be set to 0. This makes the reading more accurate. Is an instrument used to measure atmospheric pressure. Barometers can be broadly classified into two types: liquid barometers and aneroid barometers. The word aneroid means without liquid. The aneroid barometer is so named because it does not use any liquid. Let's look at components of an aneroid barometer. An aneroid barometer uses a small, flexible, partially evacuated metal box called an aneroid cell. The top surface is made of a corrugated metallic sheet and acts as a diaphragm. The metallic box expands or contracts in accordance with the changes in the atmospheric pressure. The resulting movements of the diaphragm are magnified with the help of a system of levers. The central lever of the system of levers is fixed at the middle of the diaphragm. One end of the central lever is connected to a spring. The spring prevents the evacuated metallic box from collapsing. The other end of the central lever is connected to the other levers of the system. The system of levers is further connected to a chain that passes over a pulley. A pointer that moves over a calibrated circular scale is attached to the pulley. The system of levers, the chain and the pulley helps transfer the motion of the diaphragm to the pointer on the circular scale. A hairspring is attached to the pulley to bring the pointer back to its normal position. The circular scale is calibrated to note the reading of atmospheric pressure directly. Let us now study the working of the aneroid barometer. Small changes in external air pressure cause the cell to expand or contract. This expansion and contraction drives the levers such that the tiny movements of the diaphragm are amplified and displayed on the face of the aneroid barometer. If the atmospheric pressure increases, it pushes the diaphragm downward. The motion of the diaphragm makes the central lever move in the downward direction. This small motion of the central lever is magnified by the system of levers and the metallic chain is pulled. The metallic chain, in turn, rotates the pulley and makes the pointer move on the scale. Since the scale is calibrated, the atmospheric pressure can be directly noted. When the atmospheric pressure decreases, the metallic box expands and the chain across the pulley loosens. The hairspring connected to the pulley helps the pointer adjust itself to the new atmospheric pressure. Aneroid barometers have some advantages over liquid barometers. An aneroid barometer is light and portable and can be fixed in any plane. It is calibrated to read atmospheric pressure directly. No prior adjustments are necessary. An aneroid barometer does not contain any liquid, and hence there is no fear of the liquid spilling over. Surrounded by an envelope of air known as the atmosphere. This atmospheric air extends up to 300 km above the Earth's surface and clings to the Earth due to gravity. The atmospheric air exerts a force on all the objects in the atmosphere and on the Earth. The force or thrust exerted by the atmospheric air on a unit area is defined as atmospheric pressure. The approximate value of atmospheric pressure on the Earth's surface is 1.013 multiplied by 10 raised to the power 5 Pascal. The atmospheric pressure at a point is the same in all directions. We can demonstrate the presence of atmospheric pressure with a simple experiment. First, pour some water into an empty can. Then heat the can till the water starts turning into steam. Next, stop heating the can and close the can using a lid. Now, pour some cold water on the can. You will observe that the can gets crumpled. This is because when cold water is poured on the can, the vapor inside the can condenses, creating a vacuum. The atmospheric pressure outside the can then crushes its sides. What is the strength of atmospheric pressure? Consider a sphere made of two hollow hemispheres, each of radius 0.5 meter. The air inside the sphere is removed and the hemispheres are pressed together by atmospheric pressure, which is equal to 1 multiplied by 10 raised to the power 5 Pascal. Now, if the two hemispheres were to be separated, the minimum force required would be the product of the atmospheric pressure and the area of one hemisphere. Substituting the values and simplifying, we get the value of the force F as 1,57,143 Newton. The atmosphere exerts pressure on every object, including humans. However, we don't feel the effects of atmospheric pressure as our blood exerts pressure, known as blood pressure, to counter the atmospheric pressure. To understand this better, let's look at one more common example of atmospheric pressure from everyday life. While sipping a drink with a straw, the air inside the straw is inhaled into the lungs, reducing the air pressure in the straw. However, the atmospheric pressure acting on the surface of the drink in the tumbler remains the same and forces the liquid up the straw. Other applications of atmospheric pressure are the working of a syringe, a rubber sucker, a siphon system, and a lift pump. The phenomenon of atmospheric pressure on the Earth is due to the presence of the atmospheric air surrounding it. On the Moon, however, there is no air, and hence no concept of atmospheric pressure. The Earth's atmospheric pressure at any given place can be measured using an instrument called the barometer, invented by Torricelli. A simple barometer consists of a glass tube of length 100 cm with one end closed and a trough with mercury. The tube is completely filled with pure and dry mercury. Its open end is closed with a thumb and inverted vertically in the trough filled with mercury. It is observed that some of the mercury from the glass tube flows down into the trough, and a fixed length of mercury column remains in the tube. The empty space above the mercury column is called torricellian vacuum. Let us consider 2 points, A and B, on the surface of the mercury. Note that both the points are at the same horizontal surface. There is air above point A and the mercury column above point B. PA is the pressure exerted by the atmosphere at point A, and PB is the pressure exerted by the height of the mercury column in the tube at point B. Since A and B are on the same horizontal plane, PA is equal to PB. Therefore, the atmospheric pressure is expressed in terms of the length of the mercury column. The atmospheric pressure at sea level is 76 centimeter of mercury. The SI unit for atmospheric pressure is Pascal. Let's calculate the atmospheric pressure at sea level in Pascal. The atmospheric pressure is equal to the pressure exerted by a mercury column of height h. The atmospheric pressure is equal to the product of the height of the mercury column, the density of mercury and the acceleration due to gravity. This is equal to 1,01,293 Pascal. Example 1. Instead of mercury, if iodine of density 4,920 kg per cubic meter is used in a barometer, then what will be the length of the iodine column if the atmospheric pressure is 76 centimeter of mercury? Let the height of the iodine column be h. Pressure exerted by iodine column is equal to pressure exerted by 0.76 meter of mercury. Substituting and simplifying the values, we get the height of iodine column as 2.1 meter. Mercury is used as a barometric liquid because its density is the highest among liquids. It is readily available in pure and dry form. At normal temperatures, its vapor pressure is negligible. Hence, there are no mercury vapors above the mercury column. It is easy to note mercury readings because it is a shiny and an opaque metal, and it does not stick to the sides of the glass tube. This brings us to the end of the introductory module on atmospheric pressure.
Extends above the Earth's surface in different layers is called the atmosphere. The pressure exerted by the atmosphere is called atmospheric pressure. Air exerts pressure as it has weight. Air pressure is the highest at the sea level. Although air exerts pressure on our body from all sides, we are not aware of it because the blood in our body exerts an equal and opposite pressure from the inside. Air pressure decreases at higher altitudes because the height of the air column decreases, which causes a linear decrease in air pressure. Air pressure decreases at higher altitudes also because the density of air decreases. Air pressure decreases by about 3% for every 1,000 feet of increase in height. For example, on the Great Mount Everest, atmospheric pressure is only 30% of the atmospheric pressure at sea level. As air pressure decreases in hilly areas, we can feel our ears pop, which happens in order to balance the pressure inside and outside our body. The decrease in air pressure may cause the nose to bleed, especially if the individual has high blood pressure. This is because the air pressure cannot completely counterbalance the blood pressure, causing the blood vessels in the nose to rupture. That is why doctors advise blood pressure patients to avoid going to hill stations. So, what about aircraft? Why doesn't your nose bleed when you fly in an aeroplane? This is because aircrafts have pressurized cabins that have sufficient air pressure to safeguard the passengers. Thus, atmospheric pressure decreases with altitude due to decrease in the height of the air column, which causes a linear decrease in atmospheric pressure. Decrease in the density of air, which leads to a decrease in atmospheric pressure.
Small element of fluid in the form of a right-angled prism. A, B, C, D, E, F. Inside a fluid at rest. As the element is very small, every part of it is considered at the same depth, and hence the effect of gravity is the same at all points of the fluid element. We know that the force exerted by the rest of the fluid on the element is normal to the surface. Let Fa, Fb and Fc be the normal forces acting on the three rectangular surfaces of the prismatic element. AA, AB and AC represent the areas of the faces BE, FC, AD, FC and ADEB of the element respectively. PA, PB and PC represent the pressures acting on the areas AA, AB and AC. Geometrically, in the right-angled triangle ABC, BC is equal to AC cosine theta and AB is equal to AC sine theta. The forces shown are normal to the respective areas that include the sides. Thus, we have FB sine theta is equal to FC and FB cosine theta is equal to FA. Let us call this equation 1. As the thickness of the prismatic element FC is constant, the areas of the three sides of the prism can be expressed in terms of the trigonometric ratios as shown for the forces given by equation 2, which is AB sine theta is equal to AC and AB cosine theta is equal to AA. Dividing equation 1 by equation 2, we get FB divided by AB is equal to FC divided by AC, which is equal to FA divided by AA. However, the ratio of force to area is equal to pressure. Thus, PA is equal to PB, which is equal to PC. Hence, we can conclude that the force against any area within a fluid at rest and under pressure is normal to the area irrespective of the orientation of the area. The pressure exerted at a point by a fluid at rest is equal in all directions. Hence, pressure is a scalar even though it is in the ratio of force, which is in general a vector to area. This is what Blaise Pascal postulated as Pascal's law. Pascal's law states that when external pressure is applied at a point in a fluid contained in a vessel, it is transmitted undiminished and equally in all directions. Let us understand it in detail using an activity. Consider a spherical vessel containing 4 cylindrical tubes A, B, C and D of area of cross-section A, 2A, 3A and 4A. Each of these openings is fitted with an airtight piston. Let piston A be pushed with a force F. Then the pressure on the piston is F by A. Pistons B, C and D move out due to this pressure. However, pistons B, C and D can be held in their position only when the forces applied on them, that is, FB, FC and FD are equal to 2F, 3F and 4F respectively. Then the pressure acting at B, C and D is 2F by 2A, 3F by 3A and 4F by 4A respectively, where each is equal to F by A. This experiment demonstrates that the pressure is transmitted undiminished in all the directions, which proves Pascal's law. A number of devices such as a hydraulic lift, hydraulic press and hydraulic brakes work according to this law. Let us look at each of them in detail. A hydraulic lift is used to lift or support heavy objects. It consists of 2 cylinders fitted with airtight pistons of varying cross-sectional areas. The 2 cylinders are connected to each other with a horizontal pipe, where the container is filled with an incompressible liquid. The load to be lifted is placed on the piston of larger cross-sectional area, A2. Let a downward force F1 be applied on the smaller piston A1. According to Pascal's law, this pressure F1 divided by A1 is transmitted equally to the piston, where A1 is the area of cross-section of the smaller piston. As this pressure is transmitted equally to the large piston, the upward force F2 acting on the load is equal to the product of the pressure and area of cross-section of the larger piston A2. As A2 is greater than A1, we have F2 greater than F1. Thus, with a very small force, heavy objects can be lifted using a hydraulic lift. The work done by the smaller force is equal to the work done by the larger force, as the displacement of the smaller piston is greater than that of the larger one. Here, the force F1 applied on the smaller piston is called the effort, and F2, the force required to lift the heavy object, is called the load. By definition, the mechanical advantage of a machine is the ratio of load F2 to effort F1. Substituting F2 with PA2 and F1 with PA1, we get the mechanical advantage as A2 by A1. Hence, we can write the mechanical advantage of a hydraulic lift as the ratio of the cross-sectional area of a larger piston to that of a smaller piston. Let us now study a hydraulic press. A hydraulic press is a mechanical machine used to lift or compress large loads. The schematic representation of a hydraulic press that works on force applied manually is as shown. In this machine, a smaller force applied on a column of liquid is converted into a much larger force acting on the load placed on another column of the liquid, connected to the first column. A hydraulic press consists of two cylinders, C1 and C2, fitted with pistons P1 and P2, and valves V1 and V2 connected with tube T1. Tube T2 connects the cylinder C2 with a water reservoir through a release valve, RV. Piston P2 is a platform at the top of which the substance to be compressed is placed. Piston P1 is raised upwards by the application of force F at the handle edge of the lever. Upon the action of the handle, the valve V1 opens. The water from the reservoir is sucked into the cylinder C1. During this process, valve V2 remains closed. When piston P1 is pressed down, valve V2 is opened. Valve V1 is closed and the water is pushed from cylinder C1 to cylinder C2 through T1. Due to water pressure, piston P2 moves up, compressing the load between the platform P and the rigid ceiling. To release the pressed substance, the release valve RV is opened to allow the water back to the reservoir. Another device that conforms to Pascal's law is a hydraulic brake used in automotives. A hydraulic brake consists of a master cylinder M, filled with brake oil and provided with an airtight frictionless piston P. Through a lever system, the piston is connected to the brake pedal F. Through a tube T, the master cylinder is connected to a wheel cylinder C, consisting of two pistons P1 and P2, which are connected to brake shoes S1 and S2. The same system is connected to the other wheels of a vehicle. When the brake pedal is pressed, the lever system operates, transferring the force to the piston P. The piston P is pushed inward, increasing the pressure in the master cylinder. According to Pascal's law, this pressure is transmitted to pistons P1 and P2 in the wheel cylinder. These pistons force the brake shoes S1 and S2 to move away from each other, which in turn press against the inner rim of the wheel. Hence, the brake works and retards the motion of the wheel. When the pressure is released, the brake shoes return to their normal positions with the help of a spring mechanism.